Okay. Okay, can everyone hear me okay? I got the mic on, yeah?
Yeah, because they're recording you. That's
Okay, very good. Okay, so here we go. The second part of this, which is basically energetic particles in the heliosphere. There's some a little bit more heavy-duty math in the middle, but a lot of just showing some pictures of what's out there and what's going on as far as energetic particles are concerned. Okay, all right. Let me first. This is sort of a drawing I made of our heliosphere, at least one segment of it, and again to show some of the populations that we'll be talking about, the main culprits and energetic particles. Here's the sun. Of course, you get solar energetic particle events coming. They come in a couple of varieties, these big gradual events and impulsive events. We'll talk more about those. At Earth, if this is Earth's magnetosphere, we get when these shocks go by Earth, you get energetic storm particle events. These same shocks that are often being driven by the CME, they come past Earth, and you'll actually get these energetic storm particle events, which are associated with the shock when it passes Earth. The planets themselves, because they have shocks, I mentioned to them, as the solar wind has to go around the magnetosphere, it has a big bow shock all the way around. I'll show some pictures of that. There's a lot of energetic particle activity there, and of course for us it's very close to home. We can study it very well, and lots of missions have been up there to study our own energetic particles. Co-rotating interaction regions, I mentioned some of these shocks pairs that occur when fast wind overtakes slow wind and squeezes the gas in between and creates usually a pair of shocks when you go further out. The galactic cosmic rays are, of course, not from our system, but they certainly come into our solar system, and we'll talk a little bit about them near the end, where they come from. There are these things called global merged interaction regions, which kind of occur when you have many solar events during solar active regions, where several shock events and energetic particle events, and they tend to coalesce, so that when you get out into the distant heliosphere, they kind of coalesce into some big events rather than individual single events that we would see closer to the sun. And then finally, there's the anomalous component, which are particles, and I kind of got launched into that a little bit, but not. We'll talk about that. That's a very interesting case, and that's accelerated at the solar wind termination shock. Okay, so there's a whole bunch of populations, and each one has its own story in a sense, its own configuration. Okay, here are some of the characteristic energy spectra. Here's kinetic energy, MeV per nucleon. So here's a GeV. This is, of course, only cosmic ray energies. Solar energetic particles, of course, they're transient, but they can get up to GeV, so really relativistic protons. Here are some of the co-rotating interaction region events are down here, energetic storm particle events, and yeah, those are pretty much. Okay. Okay, just to make some examples to see a little bit what they look like. This is, of course, you show the most dramatic cases. This is an incredible sequence of, I don't know, what is it, October 26th to November 7th in 2003. This is the so-called Halloween events. They occurred during Halloween. And you see here that you get all these events, 1, 2, 3, 4, 5, 6, a huge number of events that came from an active region on the sun. As the sun rotated, it kept spewing out from different events. You see they have the sort of characteristic rise time and decay, rise times of maybe a couple hours from a flare, associated with the active region, and then a day or so or two later, you get the shock produced at Earth, and the particles tend to peak at the shock when it comes by. And here's the flare, X10, here's the shock, and so forth. And this one was actually very dramatic. In fact, it was interesting because I happened to be out giving candy to trick-or-treaters at my house in Durham, New Hampshire, which we tend not to see northern lights. But suddenly the sky got very red, and I said, what's going on? And I later found out, yes, that this was northern lights in Durham, New Hampshire, which is not a common occurrence. So it was very active. Okay, here's, so those would be what would be called the Halloween events, large gradual events. They tend to be driven by coronal mass ejections, large, strong, extended shocks. There's other type of solar energetic particle event which are called impulsive events. Oh gosh, that got covered up some. These are just called impulsive events. And they tend to just, you can see from their pattern here, this is time and this is energy. So the high energies up here arrive first, low energies last, so they don't scatter much. They basically just come out by following field lines. They're much smaller events. They're up to, up to an MeV perhaps, but not much beyond. And so they're presumably coming from the flare site on the sun, that presumably from magnetic reconnection, but these events are very hard to really understand their acceleration mechanism. They were discussed at the recent SHINE meeting, and there's all kinds of ideas. One of the things that characterizes them often is strange composition. For example, they're known to have often a much higher composition in helium-3 of all things than the solar atmosphere has. And so, the most likely reason for that is plasma interactions, where helium-3, because of its unusual mass to charge ratio, sort of resonates with different waves than any other ion. And so most people think in terms of some kind of plasma acceleration mechanism, or at least selection mechanism, before they are later further accelerated in a reconnection site or a shock. But these are the probably the most mysterious events. But they're quite common, but they're not very large, so they don't create real space weather effects. Here's one of these co-rotating interaction region events. So you have here we have it. Here's the speed. So you have the slow wind ahead of the event. You have here's the fast wind later on following, pushing into the slow wind, and you squeeze this area in between. Okay, you see it has a big enhancement in the magnetic field where you've squeezed that plasma. It's got an intermediate velocity, and there's two shocks, a forward shock and a reverse shock. Okay, and you can see in the energetic particles, which are plotted here for number of energies, particles which peak at the two shocks, and with a large enhancement. And so that's another type of event. Right, and this usually happens when you're not during solar maximum conditions, but where you have high-speed wind and low-speed wind. The high-speed wind is sort of in a well-defined area from the sun, and then through rotation, you find that the fast wind can trail the slow wind. Okay, let's talk about particle acceleration mechanisms. The starting point is, of course, electric fields. Magnetic fields don't accelerate particles, so you're really stuck with the electric field. But the restriction in most parts of our space plasma environment, and I'm sure you've heard of this before, is that the electric field tends to be close to -1/c V cross B, so that the electric field in the plasma frame is close to zero. Essentially, that's because electrons are mobile, they can short circuit electric fields. It's not always true if you have very underdense parts of the environment. For example, in Earth's magnetosphere, it's when you have auroral situations and you're accelerating particles with electric fields down into the top of the Earth's atmosphere, what happens there that breaks this relationship is there are very few charge carriers, which are not enough to really short circuit the electric field, which is imposed by mass motions elsewhere in the magnetosphere. But in the things we're considering here, this is almost always satisfied. And so the acceleration really depends on on velocities of the plasma. And not just a constant velocity. If it were constant velocity, you could step into that frame and then you'd have no electric field, okay? So it's variations in the bulk velocity of the gases that are doing the job. And of course, so if you have gradients, like if you have a CME, obviously it's moving compared to through the background solar wind, and so now there's a gradient in the velocity, and then you have potential for acceleration. So, and this brings us back to the origins of the ideas on particle acceleration here, which is due to Enrico Fermi, who actually came up with the sort of classical ideas I'm sure you've probably heard of first order and second order Fermi acceleration. And again, based on mass motions which are not uniform, okay? And the first order and second order, and this is very early on. This, of course, prior Parker's solar wind thing was 57, so this is quite early on. And the basic idea can be drawn in this sort of a picture like this. If you have, say, scattering centers, if you have the little black circles as particles, let's say, and if you have elements of fluid, okay, elements of the bulk flow of the plasma, if they all tend to be converging on each other, as I've drawn here, you can have a situation, and anyway, Fermi described this in terms of clouds maybe out in the galaxy. He was more interested in the galactic cosmic ray issue and how we accelerate galactic cosmic rays, but where you might have a convergence of clouds, and then of course particles bouncing between the clouds are like a ping pong ball bouncing between approaching ping pong paddles, and you get accelerated on each bounce. And so then you have the systematic, and i.e. a first order effect. And then the second idea was that you have these balls moving in all different directions, okay? And so you can imagine here you have then a less efficient process because particles interact with one of these spheres. It might be an overtaking collision, in which case you gain energy, but then it might be a going away collision in which you overtake the object and bounce off it, and then you lose energy. And then statistically, you either bounce off it, you happen to have more head-on collisions than overtaking, and then you gain energy, but you might also lose as well. So this is a second order, that is second order in, let's say, this particle speed of the efficiency of the mechanism going like a power of V over C, okay? So if it's second order, it's a much slower process than if it's first order. Okay, so those were the two classical mechanisms. I mean, in Fermi's mind, this was like clouds in the interstellar medium, moving in all different directions and particles bouncing around between them. I think he envisions for the first order process that you happen to have a magnetic field, say, connecting two clouds which are approaching, and so particles kind of go back and forth, confined by that magnetic flux tube, and systematically gain energy on each encounter. But that was a bit contrived, and I don't, that didn't have too much traction, but so I'll come back to this. Whereas the picture bouncing off clouds going random motions, that was sort of at least a well-defined potential process. And he actually suggested that galactic cosmic rays were accelerated in that way. Okay. All right, so those are the two basic mechanisms. And the question now is, how do you sort of construct transport equations to, treat these kinds of processes, rigorously. Okay, now, so this is sort of the mathematical part. And of course, the starting point, the most part is, well, it almost essentially has to be your starting point, is the Vlasov equation. If you're in a plasma, and you probably are all familiar with the Vlasov equation, it's kind of the collision-free Boltzmann equation, all right? It basically, it's Liouville's theorem. F is conserved if you follow the particle trajectory, right? And it's where, dx dt is given by v and dp dt is given by this quantity. So it's really just a restatement of Newton's laws under these fields. Now, you might say this is really the starting point, but it isn't really, because this is a one-particle distribution function. And so this is actually a reversible equation. Okay, it conserves entropy. It has no collisions in it. Okay, and so these electric and magnetic fields in this picture would be given by just the average fields created by all the other particles. But it does not include fluctuations in E and B due to the fact that the particle you're talking about came very close to another particle and therefore got collided with it. Okay, so this is really, and this is the limit. So this equation you would start out with in the limit of either a very tenuous gas, so collisions are very rare, or the way you can look at it is if you took a plasma that had some density and then you started cutting in half all the charged particles, the positively charged and negatively charged particles, and you kept making a finer and finer and finer cuts. It turns out that then no one particle would have enough charge to really substantially modify these electric and magnetic fields, because you cut them into small parts so often, and you learn. And the way they would say that is you eliminate the graininess of matter. It becomes almost just like a fluid. And in that case, you get to the case of entropy conserving and the irrelevance of collisions, and this would be your starting point. So you have to be a little bit careful. But in most space plasma applications, this would be a natural starting point, certainly in the solar wind, where collisions are unimportant. So if you got down closer to the sun, very close to the sun and deep down the corona, then you'd be in trouble here. But that's not what we'll consider. So in my career, for example, this is the base equation I always start from. So, but there's even with this though, there's a bewildering, I mean, this is actually a very complicated equation, obviously. It's, 3 px, py, pz, x, y, z, and t, and, it's, you wouldn't start here. You try to have something much more simple that is really appropriate for the application you have in mind. So, okay, so let me, how do we proceed? And again, I have in mind now trying to understand these particles accelerated by shocks, or actually, let's say the behavior of galactic cosmic rays in the heliosphere, how that works. And in fact, what I want to do is get at a derivation of Parker's transport equation, which has really been a workhorse. Same Parker that came up with the solar wind, so he was an amazing person. In 1965, he came up with the transport equation. A little bit by intuition, by really excellent intuition, but which has been a workhorse and has had many incredible applications. So I think it's, if you work in this area at all, the Parker's equation, and also an equation called the focus transport equation, which you'll come across a lot. And so I think it's something you want to have heard about and sort of kind of know more or less how the derivation goes. So let me, I think what I will do here in the next, say, 6 or 7 view graphs is sort of run through that, not view graphs, slides, I should say. See, I'm old-fashioned, but is run through those derivations. Then you have this, because you'll have this, these slides. And so you have that as a reference, and that should be helpful for you. Okay, so let me start out. Okay, if you, I'm first going to try to derive what's called the focus transport equation. And that is that you imagine that you have a radial field, okay, in the solar wind. So radial field, and let's take the case of the magnetic field, which is also radial, okay? So V cross B is 0, so there's no electric field, okay? So in the inertial frame, the energy is conserved, okay? Now, the other thing is that I'm going to assume that the particle, and this is true for virtually all these particles, unless they get to super high energies like galactic cosmic rays near the sun, you might have trouble. But assume that the gyration, the radius of gyration, is small compared to the characteristic radial distance here, okay? So that when particles are, the variation over a gyro radius of the particles is small. It turns out then I'm able to use as a conserved quantity the magnetic moment of the particles. And you've probably heard of the magnetic moment. Again, this is the thing that describes, for example, and it's given by, I'll do non-relativistic just for simplicity here, V perp squared, this is the velocity component perpendicular to the field, over B, is a conserved quantity under these circumstances. And this is the quantity, for example, which shows you that when a particle moves into a region of larger magnetic field, it also goes to larger V perpendicular, and eventually it can mirror and come back, okay? So that's the quantity that's conserved. Okay, if that's true, and also the electric field in the inertial frame is conserved, and I can write that this way, but I want to express the velocity, okay, the speed, and the cosine of the pitch angle, mu here, in the fluid frame, okay? And the fluid's moving out at a constant solar wind speed, okay? So that's why this is not just V squared, the energy. It's got, E, except for half m, So I want that in the fluid frame, and I'll come back to that because you'll see why in a bit. So this is the conserved energy in the inertial frame. And then if you have a transport equation like this, that basically F is constant along, so each particle is very deterministic. Exactly, if it starts out here with some speed and a pitch angle, it moves in a very definite way. It will move out in radial distance. It will change its pitch angle, and it will change its speed in the plasma frame, okay? So you can just write that this way. The total change of F, dF dt, as you follow that trajectory, moving out, gyrating out, is 0, unless there's scattering. So I'm going to come back to scattering in a second. But if there's no scattering, F is 0 by Liouville's theorem, and you simply write this as dF dt, or taking the total derivative, or dF dr dr dt, dF d mu dt, dF dv dv dt. That tells you, and that whole, if you take all those accounts into account, it should be 0 if there's no scattering. Okay, so using now these relationships, and you may probably want to work through this on your own, but it's quite straightforward. So these are both conserved. And then what you know is that first derivative, dr dt, is certainly just the speed of the wind plus, in the frame of the wind, the radial speed, radial velocity component of the particle, which is v mu. It's the speed in the wind frame times the cosine of the pitch angle, okay? So we know that's true. And then, using those two conserved quantities I had before, the magnetic moment and the energy in the inertial frame, I can calculate these coefficients in front of the other two terms. So I end up with this transport equation, which tells me how, if there's no scattering, how a particle's distribution, and what its, its weighting is, how many particles per cubic centimeter and so forth, and as a function of velocity, along that little that wedge of solar wind going out. And here it is. So I've got those coefficients. And now I put in the scattering. Because, as we've talked about, there's lots of fluctuations in the wind. Particles don't go in nice, smooth trajectories. They do get scattered. And so I have to put in a scattering term. OK, what about the scattering? OK, I'm showing this, and basically, let me tell you before I kind of go through this, because I think this is kind of just interesting. The mu value, okay, if you scatter in pitch angle, and again, the little subtleties of whether you're at the scattering off alphane waves, going a little faster or a little slower, that's irrelevant for this purpose. You're basically scattering approximately elastically in the solar wind frame. And therefore, your mu value, the cosine of the pitch angle, is just scattering at random. And so let me, how do you see that that's what happens in a scattering process? Okay, I will show this partly because, again, it goes back to Gene Parker, who has done so many things in this field. And the idea here is that suppose you have a magnetic field which is one-dimensional, okay? So it's mostly a constant in this direction, but it has components in these two directions, all right? Okay, so it has I and j components, okay. But it only depends on z, okay? All right, now, what I'm going to do is choose, so you have a background field B naught, and I superpose upon it two little, helical fluctuations in the magnetic field, okay? Together, these form a helical fluctuation. There's a part that's in the x direction, parts in the y direction. I'll draw a picture of what this little helical packet of alphane waves looks like. It's kind of a length L. It has a exponential fall off away from z equals 0, okay, and it has a magnitude epsilon. And the question is, so I've constructed a little, constructed something like that. So this is what, I'm going to send this particle through such a little wiggle here, all right? And the question is, and I'm going to do it, I'm going to look in the frame of the alphane speed. So I'm going to look in the frame of the wiggle. So this wiggle's not moving in the frame I'm looking at this. But a particle's going to come in, gyrate somehow around this field line. And this wiggle, by the way, is just not on one field line. It's on all the neighboring field lines, too. So the whole fluid is kind of going back and forth like this, but it only has this finite extent. OK, so the question is, what happens to the particle? OK? And you're going to assume this is a small amplitude. OK? And this is what Parker, this is what Parker, just a second. OK. So this is what Parker basically did. All he did with a linearly polarized thing, and I actually put in the circular polarized piece because it's a little bit easier. OK, so what happens is, when you send the particle through, when you use kind of a Born approximation, so even though the particle's getting slightly scattered, when you calculate that scattering amount, you assume that its velocity does not change. So it's a Born approximation. You actually get a really cute little result. And this is exercise 2, by the way. So you have access to this and the solution and stuff, but you can play with it yourself. And you find that you find an interesting result. That what happens, of course, in the frame of the wave, it can't change its energy. So the only thing you can really change is the change in the z component of the velocity, okay, and also the perpendicular piece, of course. So you can change, so this is, if you divide this by v, of course, it's just mu, cosine of the pitch angle, okay? So the change in the cosine of the pitch angle after the particle's gone through this little wiggle. And it has the following properties. It has some interesting properties. Let's see, it has the length. I'm getting myself confused. I think L was the length of the whole packet. Obviously, the longer the packet, the more the change. It has, but this is an interesting one. You'll notice that unless you satisfy this condition, okay, then the effect will be exponentially small, all right? And so in order to have effective scattering, you need to satisfy this quantity vanishes, or close to vanishes. And this is the so-called resonance condition. And you can see, actually, this is the cyclotron resonance condition, okay? This is the condition that the particle gyrates, goes through one gyration during one wavelength of that little wave packet. And so that, of course, is the cyclotron resonance condition, which we talked about before. You need to satisfy that for effective scattering. Not exactly, of course. If you're a little off the resonance, this will be a little away from zero, and you'll get perhaps a little slightly less effective scattering, but that's okay. Okay, but the thing that's important here is this cosine of phi. Phi is the phase shift between the particle's gyration and the wave's gyration. And so depending on that value of cosine phi, this can be positive or negative, okay? With equal, and it's a cosine, so you're equally likely on average. If you just, so the idea is here, if you now run a particle through a bunch of little wiggles like this, one after another, it'll do a random walk in basically plus and minus each time, so it'll get an increase by a small amount in its pitch angle or a decrease. And so you can imagine that this will experience a random walk or a diffusion in the quantity mu. Okay? So so what this process leads you to say is that you expect such a particle to have pitch angle diffusion. Okay? But I think this is kind of a nice way to see why it is that you get this sort of diffusion in pitch angle. Okay, so as a result, I'm going to simply put the diffusion operator on the right-hand side in basically spherical coordinates, or I'm for mu, or cylindrical, right? This is Vz over V. And this is the way it looks, and this is the pitch angle diffusion coefficient. And actually, there's ways you can calculate this from sort of quasi-linear theory, and we won't go into that here. But that's a pretty well-defined process. So this is, if I've combined that with what I had before for the special case in which V and the magnetic field and solar wind are aligned, and this is what's called the focus transport equation, which is something you'll run into a lot of the time if you're dealing with particles which can be somewhat, they're not close to isotropy. So this allows for beams moving along the magnetic field or somewhat wide beams, but you're not close to isotropy in this case. So this is a fairly general case. And the terms that are important here, for example, focus, the reason it's called the focus transport equation is this term here. This is the term that focuses, if you go into a weakening magnetic field, the particles focus towards propagation along the magnetic field. Or in the opposite case, if you go towards a stronger field, you're mirrored essentially into a broader distribution in pitch angle. Okay, so that's the focusing term. This is a term which eventually will lead to deceleration because it's got a df/dv. Okay, because you're moving in an expanding medium, you are losing energy as you do work on the flow. And so this doesn't have a simple form, as we'll see later in the Parker equation, because this does not demand a nearly isotropic distribution. So this is the beginnings of energy loss in an expanding flow. Okay, and this is just the convective derivative, okay? And so that's the focus transport equation. And it's kind of a workhorse in certain parts of this field. And actually, just to show you that it can kind of be kind of cute, is my PhD student, worked out an approximate, boy, this has got messed up, didn't it? Here. Oh, well. kind of a calculation of that in the approximation that you let particles off near the sun at a particular time, and then you let them propagate out along the magnetic field, but of course, slowly they get scattered, and the scattered particles are scattered back, and therefore they fall behind the particles that weren't scattered. And so you can calculate what the front of that little delta function, which you put in at the sun, you can calculate how that will look when that front moves by you. You'll get just a very few particles here that have not scattered at all, but then rapidly you get some that have scattered somewhat, and then it actually falls off like this. It's because some of the ones that are scattered too much, they fall way behind. So you get pulses coming through rather than, which is a little bit contrary to expectation. Okay, so that's the focus transport equation. Now, the reason I decided to do it this way was the focus transport equation is, as I say, a workhorse. You'll see it run into a lot if you do this kind of work. Now, what we can now do, once we've got the focus transport equation, we can say, well, let's assume the scattering is very efficient. So this d mu mu thing is really large, so you're scattering particles like mad. And then let's average. So let's assume this distribution, sorry, the one in the focus transport equation, the one I just, is nearly isotropic. So what I can then do is take little f, I will average over, I'll multiply by d mu and then integrate. Okay, so I'm going to look at the sort of the isotropic piece here. So I'm going to call f is the average, right? But I'm assuming very effective scattering. And when I do that through the focus transport equation, just multiply by d mu. I do some integration by parts, unlike the term's got a d by d mu in it, and I fiddle around a little bit. I suddenly come out with this version from the focus transport equation. And by the way, notice that when I integrate over mu, the scattering term's gone because it has a d by d mu in front, and therefore it just vanishes. And I get something that looks like this. Okay, and that's exact. And this is sort of now looking a bit like the so-called Parker equation for nearly isotropic distributions, but not quite, because you'll notice that this only has a radial dependence in it. And that's because the problem I set up with the focus transport equation, particles all moved out a particular radial velocity. They couldn't scatter across it. They're only scattering in pitch angle. So what I then do is simply let's just generalize this to a three-dimensional geometry. So clearly, this becomes v dot grad, okay? This is clearly del. This is clearly the divergence of the, now in this case it's just the r radial piece, but now if I generalize it to a sort of generally 3 dimensions, this will be the vector s. So I have divergence of s. And s again is the streaming. It's the function, of mu v times f. Okay, so it's the differential flux. Differential because you haven't integrated over the speeds or the velocity, the speed distribution. Okay, and here this 2v over r is just the divergence of the solar wind, grad dot the divergence here, and then v df dv. And now, so this is actually, except that I haven't said what s is, this is actually the equation Parker wrote down in 1965, which he originally kind of did for, I think, getting treating the modulation of cosmic rays trying to come into the heliosphere. Okay, so but we're still not done because we don't have s here. How do you know what this streaming function is? This is like the differential flux, if you will. Okay. All right. So what you can do, first of all, you go back to the focus transport equation. I won't be too detailed here, others will get bogged down. But if you look at the big, what you want to do is, if you have rapid scattering, d mu mu is big. Okay, so this is a large term. And you look back here, what can balance this term? Well, it turns out when you go to, rapid scattering, the time scales, things evolve in a slower time scale because you got averaged out over particles are basically nearly isotropic, so they, the things change slowly. But this term here is the big one, the v mu dfdr, because it's got the particle speed in it. Okay, and the particle speed here is huge. All right, these are energetic particles. So the dominant terms here are this one, the v mu, and the scattering one. And so all you do is you simply balance those two terms. And so if you balance those two terms, I've done that here, right? In the first point, it's v mu df dz. Well, I can, the capital F is nearly isotropic, so I can replace it by its average. And then on the right-hand side, I take the small non-isotropic part of the original distribution function, and I calculate what that little g is. And I go through I integrate, in mu, and I mess around, and I have some conditions I have to, the integration constants have to be chosen. And I come down here, and lo and behold, I get a term that's diffusion. I get the z component. This is along the magnetic field now. I could have put radial, but I'm trying to generalize to x, y, z here. Z is what I called previously in the special case of the focus transport equation, the radial piece, is just diffusion, is a diffusive flux, okay? And in fact, I get a relationship between spatial diffusion and pitch angle diffusion, which sort of makes sense. If pitch angle diffusion's very large, very efficient, the spatial diffusion coefficient is very small, right? If I'm continuously scanning back and forth, I can't get very far spatially along a given magnetic field line, okay? So I get a nice expression here. And then in the problem we addressed with the focus transport equation, there was no way for a particle to leave the radial field line, right? It only scattered in mu. And so I'm just going to build in, by analogy, diffusive terms which allow you to scatter across the magnetic field line. Now, these are on much less firm, this is on firm foundation. These perpendicular diffusion coefficients, there's lots of debate about these things. How do particles diffuse across magnetic fields? Do they basically follow meandering field lines that allow you to think of that motion as scattering across the average field? Do you encounter curvature and gradient drifts, which send you off the field line, the field line you started on? But in any case, essentially, though, you'll have a diffusion like this. The tricky part is actually determining these coefficients. And normally, you would say they should be the same in the two directions perpendicular to the field. Okay, so that takes care of well, I put a question mark here. Now the question is there any other contribution to streaming? And it turns out there is, and this is the so-called drift term, okay? That particles can move across field lines by drift, okay? And you've probably all had this if you've had Jackson. There's a chapter in there on curvature drift, okay, gradient drift, and also magnetization drift. Does that ring a bell? Okay, there's ways in which a particle moves along a field that's bent, it drifts off that magnetic field line it was on. Or if there's a gradient, it drifts also off the original field line it was on. And if there's a magnetization effect, which is a weird one because the particles don't go anywhere. But if you have one field line here where particles are doing this, and a neighboring field line where there's a higher density of particles, in between you actually have a flux, which is normal to the field. You see that because the particles are all going this way or this way. There's more than this way, so in between you have a net flux down. And that has to be included. It's called magnetization drift. And the way we get at that is by actually, interestingly, going back to the Vlasov equation which is basically has not been approximated. And we simply look, we simply do the integration. Okay, we multiply, we take this moment, you know, the VI moment, okay, on both sides. I'll go through this a bit hurriedly, but you do that, and then you integrate over the distribution, right? Okay, to get the sort of the nearly isotropic approximation, and then you. What you find, and this particular cross product, this dot product has a very simple form here. Phi is the phase angle about the field. And lo and behold, you get this expression, which simplifies to this, and you find a result for the, and this is the gyro frequency for the particle, the perpendicular flux. And that's true of this magnetization and curvature and gradient. It's always a flux perpendicular to the average to the field. And you actually calculate it this way. And in fact, this is exactly the expression that that was written, you know, that Dana wrote down when he was talking about cosmic ray modulation. So this is the so-called drift flux. And you can get it directly from the Vlasov equation. And so you write it down this way, okay, and okay, so so here it is. All right. Now, and the other thing is so that's S, okay, and so when I take the divergence of S, okay, remember in the Parker equation that I had written down, okay, let me see, where am I? How about I'm not losing you guys? Yeah, what I really want is del dot S, okay? So I have S here. When I take its divergence, part of it drops out because the divergence, when I do the vector identity for a cross product being and the divergence of a cross product, one part is curl of the gradient, and that's 0. And so that drops out, and lo and behold, I get something like this, which gives you basically a convective derivative. The divergence of this S perp gives you grad F times this quantity, and that we call that the drift velocity. Okay. Oh, yeah, fine. Okay. Oh, yeah. We started at what time? Oh, 1:30. Yeah, yeah. Oh, my gosh, yeah. Yeah, let's, yeah. Let me just, okay, that's good. I'm going to stop in a second. Okay, so what I then do is, so here we are. So the transport equation, if I put that drift flux in here, I include in the diffusion tensor all three pieces, the perpendicular x, perpendicular y, and z. I get this, and this is basically the full Parker transport equation. And in fact, you can write it in conservative form, which is often useful. I think this is, I don't know whether Parker did this or not, but and you'll see this is nicely conserved now. If I've got the divergence of the full streaming, okay? I've got the divergence of the full streaming, and I've got a divergence in the speed and velocity, okay? And so if I integrate, so you can see this is the df/dt is the divergence of a full streaming, including diffusive pieces, convective pieces. This is the convection term. And the reason for the third here, this doesn't look too familiar, right? Because it's got, you think it might be Vn or something, but it turns out when you have the quantity as a function of its differential, you're looking as a function of given different velocities, it has this slightly different form. And often this form goes under the term the Compton-Getting effect. So anyway, so you have to be a little bit careful here. And then you have the drift contribution, and then of course this term here, which comes from the, well, you can see up here actually, this comes from the energy gain and losses due to the convergence or divergence of the fluid field. Okay, all right, why don't we take a break, and all right, and we'll come, 5 minutes or so. Okay. It's all right? Okay. It looks a little complicated, but yeah. Okay. Yeah.
Pitch angle diffusion.
Okay, what's the drag coming
So
from?
what happens is that
Yeah,
if you
oh,
have a-
that's right, yeah. Okay, good.
So I'm wondering
Yeah.
where that physics comes in.
Drag, yeah.
If we don't keep both,
Hmm?
then what happens? I think. Because
Yeah,
very-
yeah.
what Fokker-Planck does is to slow down the particles. If
Right,
you just keep the drag, it just slow down.
right,
It
okay.
doesn't diffuse in perpendicular. Must be something I'm missing.
No, I'm trying to think, is there anything that's... This is the standard, so
This is the standard
I'm,
equation.
yeah.
I was just
And
thinking
then
about
maybe,
your focus
maybe,
transport.
yeah, right, the
before
focus,
we started-
oh, I see, yeah, I see what you're saying, yeah.
The
So,
focus transport, when you put in pitch angle diffusion on the right.
yes,
you are-
right, I see what you're saying, yeah, I see what you're saying. But, I see, so you think that, yeah, there should be, but you're not, that's interesting. So because I mean, of course, I shouldn't just, but, oh, that's good. Well, that's okay. That's a question. I mean, I don't know, but I mean, if you scatter the particles, you certainly, I think the argument would be, wouldn't it, that the background solar wind is infinitely massive, I would assume. Yeah, there's no back reaction in this, definitely not. Right, so I would say it's probably just a question of, it's like,
With the drag term just goes to zero. So
yeah, or you ignore it.
ignore it.
Because you're assuming that the bulk plasma can pick up anything in the way of momentum. Yeah, I think that's probably would be my guess.
So at the end, Fokker transport is it a 5D equation or is it a 4D equation? Because
It's four. It's got DFT. Yeah, it's
Is it 4D? Because you're keeping three spatial coordinates. What does F depend on in velocity coordinates?
Yes, it's right. You've got it. Well, again, you've integrated over the angular variables.
Yeah.
You've integrated over the mass. So there's all that's
All the
left.
angular variables are gone.
Right, they're all gone. That's right. That's right. That's right. So you're near isotropy.
The
What's
equation we tend to use in fusion physics called drift kinetic, which also doesn't have any finite Lambda radius physics.
okay?
And averages out just the gyro phase.
Just the gyro phase. Okay.
But then you're left with a 5D equation,
Right.
which is a lot easier to integrate, which is the cornerstone of everything
I
we
see.
do in
I see. Yeah. I'm actually. Yeah. I should. That would be interesting
It'd be interesting to, when
to
we
look at the
add-
differences there. Yeah.
Yeah,
It really
just-
would, because I mean, this has been around
Yeah, you said this is
so long. Yeah. It's 65, and I mean, it's been used basically everywhere in space. Physics,
I always had it in mind too.
and it's.
You give a very clear step-by-step for somebody like me to be able to follow.
Yeah. Anyway. Yeah. It's funny. I used to do this. Boy, it was complicated, and maybe there's simpler ways. But I remember kind of doing a very piecemeal thing where you took the thing, you shifted to the fluid frame, all kinds of derivatives. You messed around, and then tried to calculate each piece individually by hook or by crook. I don't know. Whereas I have to say, this business of coming from the focus transport equation, actually, I mean, it's a bit fake in a sense that, I took the radial, and I took the magnetic field and the radial piece parallel, right? And then I just, by fiat, made it.
So what
in-
I was thinking was
yeah.
that I know the drift kinetic theory.
Mhm.
So there are two versions, as you know, the drift kinetic theory and the gyrokinetic theory.
Okay,
The gyro
okay.
has FLR terms, finite Lamar radius.
Okay, okay.
Let's put that to 0 for the moment.
Okay, okay.
And so if I go to drift kinetic, then I don't have finite Lamar radius, but all that I'm doing, averaging.
Right, because that would be like the conservation of magnetic moment thing. right?
Exactly,
Okay,
exactly.
okay, okay.
And I should be able to derive from that pathway.
You should be able to.
This
We
equation.
should look at that, Matava. Yeah, that'd be good, because I hear about these equations from the turbulent guys, you know.
Yeah, yeah.
You're like, what's his name in Iowa now?
Oh, you
Oh,
mean
yeah, I'm thinking of
Greg House?
Greg House, for example. Yeah, yeah, yeah.
I'll let you talk.
Okay, okay, okay.
So is this equation is spelled in a non-relativistic?
I did non-relativistic. Yeah, I think it comes out with just P's
Ah, okay.
and instead of V.
Because what I would expect if you are going to like really high energy
Yes,
particles,
then you
can,
really should. Yeah, you really should. Yeah, it should. And I just got, yeah.
Because well, I'm also for my PhD like working with the focus
Okay,
transport equation.
okay. Are you good?
And what?
Yes, good.
Yeah. And so one of the things I was wondering, you use some kind of mixed coordinate frames, right? You use like the.
Well, let me think.
Because you have the velocity of the particle in the.
I have that in the plasma. I wanted to go to the plasma frame so I could treat pitch angle scattering in the plasma frame.
Yeah,
See,
but
that
if
was
you
the
have-
difference.
If you would have to do it.
Good question. That's a good question.
Because you
I'm
have
not
your
sure.
time in one.
Yeah.
In one
Yeah, yeah, yeah,
frame,
yeah,
and
yeah.
you should
Good.
time in-
Yeah, yeah. That's a good question. That's a good question. I should. Okay. I don't know offhand. Okay. Okay. Okay, yeah, all right. Okay, let's continue. Okay, so that is the Parker equation, and I was asked a question about the relativistic validity, and I think it's true that if you just replace you work it in terms of p, the momentum, and you replace the v by p, and of course f is now a function of p rather than v. It still holds, but I have to say I haven't gone through that recently, so I hope I'm not wrong. Okay. Anyway, this was when Parker first wrote this down. I think solar modulation of galactic cosmic rays was the area he was most interested in which the near isotropy of the particles was certainly the case. But it turned out to have application for shock acceleration. Let me, oh, by the way, I just for kind of joked, I just put this in. If you don't like all this analytical formalism, you can always do kind of you can follow particles and construct distribution functions. And the reason I always remember this picture here, this was actually for trying to model the behavior of co-rotating interaction region particles in the heliosphere when two shocks when the fast wind overtakes the slow wind. And one year they had in our section of the AGU, the SPA section, there was a competition for the worst figure in JGR, and this one actually won it. So, so I thought it was kind of entertaining. Okay, shocks and energetic particles. Okay, I listed before this slide, but with just names of particles on them, and now what I've done is I've imposed where there are shocks, and And you'll notice that there's basically shocks associated with all those particles that I mentioned to you. And so in fact, it's really the shocks that are except for the impulsive events coming from the sun, where we're really not sure, they probably come from, they may be shock associated. Maybe there's a thing called a jet shock in magnetic reconnection, which sort of, they have a reconnection site above a coronal loop, and it squirts particles down to the top of the loop, and they end in a shock. That's possible. I'm not sure I think that's the case, but because you certainly have to say, have some mechanism for getting, say, the helium-3 rich enhancement. So anyway, but everywhere else, these the particle populations I talked about are all shock associated, except for galactic cosmic rays, but it turns out I think that they're shock associated too, and we'll talk about those. I want to make sure I get to that. Okay. Okay. Let's talk about, diffusive shock acceleration. This was, if you basically take the Parker equation, okay, if you take the Parker equation and consider a 1D situation, one dimension, so things only vary in z, and you look for a time stationary configuration in which you have a velocity only in the z direction, you inject particles at z equals 0 at some momentum. You put a source term on the right-hand side, and you don't have any. The drift term doesn't come in because if it's one-dimensional, the drift is in the opposite, is in the y x direction, so the drift term doesn't come in. You only pick up the z component of the diffusion, and it's stationary, so there's no dB/dt. So this is about as simple as you can get. Here's this 1/3 dV z dz, okay? And it turns out, if you work through this, and this is exercise number 3, so this is another one of the exercises that you have access to, you find the following. You find that the distribution, so for z greater than 0, so I guess I've got, so I guess I've got the flow coming in from the left. So z greater than 0, yeah, that's the downstream region. So I must have the particles coming in from the left-hand side. And what you have is a constant in space. So downstream of the shock, you simply get a solution which is independent of z, and it's a power law in p over p naught. P naught's the injection, and p, I've used momentum here. That's fine. And I get a power law index minus beta, where beta is equal to 3 times the compression ratio over the compression ratio minus 1. And the compression ratio is the ratio of the upstream to the downstream Vz. Or actually, the compression ratio is the downstream density over the upstream density, which is, of course, equal to the upstream velocity in the z direction over the downstream, okay? And so, and of course, those two are equivalent because of conservation of mass. Anyway, so this is a characteristic index that you get that's only a property of the compression ratio of the shock. In the upstream region, okay, so z going to negative, I have an exponential growth. So z is negative. So I have exponential growth to the shock of this form, e to the v z over k, and then times the same quantity here, this power law. And this makes sense. This is a convective diffusive ramp. So upstream of the shock, you have a buildup to the downstream level of intensity or distribution function. And it's a balance between diffusion upstream and convection back to the shock, okay? And so if you have, for example, very small diffusion coefficients, that foot is very close to the shock surface. If k is very large, particles can scatter a long way upstream and then back to the shock, okay? And the physics of this is simply that particles, once they're injected into the shock, they scatter back and forth across the shock with the statistics of the scattering. I mean, some just go through the shock once and disappear downstream. Others go through the shock, then come back, but they get back. Of course, they never can stay upstream because eventually they're always swept by the flow into the shock. And so you have a collection of particles. Some have been through the shock 1 time, 3 times, 5 times, 7 times. And the statistics gives you this power law increase. Because every time you cross the shock, it's a first-order Fermi process, right? You're always scattering between converging flows. Because the converge at a shock, del dot V is negative. Okay? It's always converging. And so whenever you're scattered between those 2 flows back and forth, you always gain energy. So you remember I said that the Fermi first-order Fermi mechanism is kind of contrived for where he was looking for the process. Shocks are a natural place to find it. You have that automatically. Okay? And so this index is very special. And of course, almost immediately, I mean, people, and first of all, there were 4 papers that all very nearly the same time came out with predicting this. And of course, immediately people realized this index was very close to what would explain the galactic cosmic ray index. So it was tremendously exciting. I think these different authors did various different things. I heard about Axford, Lear, and Skadron first. They actually not only did this solution, they did a solution where you put in a power law, inject a power law, and they also looked at the nonlinear shock, where the back reaction of the energized particles provided a pressure that influenced the shock structure. Krinsky, I've kind of forgotten what his, I think his was just pretty much equivalent to this. Blandford Stryker was something like this, and Bell actually did one additional thing. He actually made an estimate of wave excitation by the particles in the upstream region, which make the process more efficient. And so I've done a lot of work in this area, so I may come back to this, but we may not have time. Interestingly, my old boss, Len Fisk, actually, when he hired me in New Hampshire, he wrote an article in 1971, way before these guys. He did his thesis on the aspects of applications of the Parker equation. And he looked at these particle enhancements at traveling shocks, but he realized that a power law gave a solution, but he imposed the value of the power law index. And he didn't let the solution dictate that power law index. So he kind of missed out on, I think, a real a coup there. What I find so interesting about this is that Parker wrote down this equation, the one on the previous view graph, in 1965, and this is 1977. So it's like 12 years of this very basic equation sitting around, and nobody came up with this in 12 years. So. And in fact, I feel bad about it because I actually worked on it myself, but I didn't realize some of the subtleties. I don't know, I don't know why I didn't, but I think other people feel like I did. It was sort of a problem that was waiting for somebody to look at, or pick up, or see the simple solution. I think I wasn't aware that. I thought I had to build in an electric field into the shock or something like that. I remember because the person I was working with as a postdoc in Germany, Heinz Folk, actually said, he was convinced, he said, the shocks in spiral arms of galaxies have to accelerate cosmic rays. Why don't you take a look at that? Maybe it comes from the Parker equation, and I don't know. There was a lost opportunity there. And I think other people probably feel as I did. So it's kind of amazing. So don't think everything's been solved. It's somehow people don't maybe look at things quite right, and so you never know. And of course, Parker himself didn't really. I guess he wasn't particularly. I know he worked on modulation of cosmic rays and also solar flare particle propagation with the Parker equation. But anyway, so. This was a huge breakthrough because, of course, the origin of galactic cosmic rays has been a huge problem for decades, and basically this solved it. There's a lot of extra complexities about cosmic rays. I'm trying to think. I'm going to have to So, but I really, this was kind of a huge move. And there's a whole research program now on trying to look at, and what most people feel now is that it's supernova explosions, the shocks generated in supernova explosions, which actually create most galactic cosmic rays. Certainly up to what's called a knee in the spectrum, which is, I don't know, is it like 1,000 GeV or something? Maybe it's higher than that. But beyond that, I think shocks have some difficulty. But you can imagine if you look at an actual supernova blast wave, you have initially a blast wave, and then the shock wave slows down. And as the shock wave slows down, there's other complexities about it. You have to sort of somehow integrate over this thing. And because the compression ratios that would go in here would change too, these X's, through the evolution of through the supernova remnants. So there are some subtleties in how you actually go about this, but I think nobody doubts that that this is the origin of galactic cosmic rays. Okay, I wanted to say, let me just do a couple. I'm just trying to think what I should do. Yeah, I mean, one thing is not in the equation, the shock acceleration equation I just put up there, because I did a one-dimensional problem. It turns out there's also a contribution to shock acceleration, which is not really Fermi, which is just bouncing between approaching walls. And that is that if you have a shock like this in the direction, not the z direction, but the going in, we had z going into the shock before. This is, if this is the magnetic field direction, particles can drift along the motional electric field, the V cross B electric field, up the shock surface like this. And in the process, they actually pick up some energy. And in fact, that comes out a little bit of a different process when you do the shock acceleration. Because we did the one-dimensional problem, it didn't make any difference. The drift term dropped out. But the drift term was recognized as a way in which shocks could accelerate particles. And only when Jacobi actually included the drift flux, which we put into the Parker equation a few slides ago, did he include this process also in the formalism of diffusive shock acceleration. So shock drifts in there. And, if you look at acceleration at a shock by different observers, you can find that each observer would have a different interpretation of how much of the acceleration was first order Fermi and how much was shock drift. So it's kind of an observer-dependent division between those two processes. Really, they're just part and parcel of the same acceleration process. Okay, I wanted to say that. I'll drop that. Let me see. I want to, let me just quickly, what I'm going to do. Let me go to the cosmic, let me see. We're essentially, let me go to the, I was going to do it too, okay. The power law index, this might be kind of interesting too. Just one of the tests, of course, of diffusive shock acceleration, if you look at, say, shock events in the interplanetary space, is whether the beta, the power law index in the energetic particles is actually what you would expect. So if you look at the power law index of the energetic particles and then you measure the X compression ratio of the shock, do they agree? Okay, and if you place various shock events in this plane with the compression ratio of the shock shown here, with the spectral index, actually this is in the momentum dependence, this would be the beta value, okay, here. You plop all the events down, and if they satisfy this condition, they should lie along this dark, solid line. And there's been a lot of discussion about why is there all this spread? And of course, you could argue that shocks vary along their surface and particles move along the shock as they go through their acceleration process. You wouldn't expect it to be one-to-one. And also a little bit more complicated is the fact that these events are very weak shocks, these little X's here, and it turns out that if you accelerate a power law of particles, so you don't just put in particles at one particular low energy, which is what we did to get this spectral index. If you take an advected power law index of source particles, which has a harder index than this, all the shock does is lift up that prescribed advected index. And so you wouldn't even expect this result to hold in such a circumstance. And so often in these very weak shocks, you have a power law of injected particles come sweeping into the shock, and of course they just get lifted up, they retain their power law index, and you wouldn't expect a correlation here. So, and some of the circles actually are kind of events that are nearly perpendicular, where you have the feeling that particles come in, bounce once off the shock and recede, and so they don't go into this whole multiple encounter process, which is characteristic of diffusive shock acceleration. And therefore, you wouldn't really expect those either to really identify, for it to work. So if you, I think, take all that into account, and the agreement's not too bad. There's a couple of other subtleties that you could try to mix in, and I won't really have time. They're in the slides here. I won't have time to really talk about them. Let's see. All right. Let's see. I know I hate to do this to you guys. I should say there's a wave excitation process here. I mentioned it, that Bell, in his paper on diffusive shock acceleration, spelled that out. And so it turns out that the accelerating particles, because they, similar to the pickup ions, when they scatter in that upstream region, they can lose energy and give it over to some of the waves. That has the advantage, they always gain the energy back when they cross the shock. But in the upstream region, they can lose some energy, give it up to the waves. The waves then make the process much more efficient, because the more waves you have, the faster you scatter back and forth. And if you go to some place, and so you end up actually with often huge wave enhancements of these shocks. And I think I've showed you some before, but let me just show you some of the kinds of wave enhancements you can get. This was a comparison between theory and experiment upstream reverse bow shock, where the predictions of the wave power, the observed wave power, correlated very well with the theoretical prediction here. So the theory, which would tell you what that enhancement in waves is, seems to work very well. But you get some monstrous waves. This is, for example, upstream reverse bow shock. You get, if you look at these waves, right, here's the, this is nothing like you have in the solar wind. Generally, this is huge. These waves have amplitudes oscillating on the order of the ambient magnetic field. So the acceleration process produces, a huge amount of turbulence, which makes it much more efficient. And in fact, eventually, when you get, I think what's interesting in the process, when you start getting waves of this amplitude, you probably can't use the kind of scattering theories that we're used to doing based on small amplitude waves, cyclotron resonance. You go through several of these no. You basically come into a wave and turn around. And in fact, what gives some support to that idea is often upstream reverse bow shock, you find these monstrous wave fluctuations called slams, which are short, large amplitude magnetic structures, which, you can see the background field might be something like 3 or 4, and suddenly you see something like this. And what causes that is that some of these waves grow so large, and as they grow larger, they can scatter more of the particles coming off the shock to the upstream waves and sending them back. And each time they scatter that massive number of waves, the massive number of particles, it forces these things to grow to huge amplitudes. And it's really amazing. I think this would be an exciting problem to look at. One of the things that happens when you have a magnetic fluctuation this large, it doesn't care what the cyclotron resonance condition says. It basically turns particles around. And so it's not selective, and therefore you can really accelerate to high energies. Okay, I got 1 or 2 minutes. Let me just say some quick words about galactic cosmic rays, because I thought I was supposed to say, I did say a couple things. Here's the big spectrum here. Energy is going up to, here's the knee. I think the idea here is that the supernova remnant shocks are supposed to be able to get you up to this knee area here. All right, so these are now, again, 10, this is an EV, right? Yeah, that's an EV. So 10 to the 9 is a gigavolt, right, down here. And so look at you have a huge number of order of magnitude. So supernova shock waves should get you up to here. People play with this. Recently, someone got the Bell, the same one of the original predictors of the process, argued that at one of these shocks with all kinds of turbulence, you actually end up increasing the magnetic field level. And that's consistent with these slams I showed you, where you really can create these massive structures. It basically just become upstream of a shock like that at a supernova remnant. You just have a massive complexity. You never could use sort of a quasi-linear treatment. And if you can do that, you make these scattering a little bit more efficient, and then you can maybe rise this up to here. But I think most people feel like you can only get up to here, and what happens with these guys is not entirely clear, but there's other shocks around. If you look into astrophysical sites, you have double radio sources that have lots, their jets are often riddled with shocks. You have galactic clusters have material flowing in which gets shocked, and you get these massive shocks surrounding these clusters of galaxies. And so there's ample opportunity, I think, to get the really large energies that you see here. Okay, and this, this is the simplest possible model for modulation. I'm sure Parker did this, although now this one is basically just keeping convection and diffusion. Particles tend to want to diffuse. Galactic cosmic rays outside our heliosphere want to diffuse in because there's less intensity inside, but they're swept out by all the irregularities in the solar wind. If you balance those two, you get what's called sort of the convection diffusion model for modulation. This doesn't include, of course, energy loss, which certainly does occur for particles coming into the heliosphere where they sense the expanding wind. But one of the examples I gave, number 4, I don't know if it's number 4, I'll check the numbers, is a more less trivial expression for modulation, including energy loss as the energetic particles move in. But in the world of a complex heliosphere with a heliosheath, which has all kinds of current sheets in it from changes in the magnetic cycles over many magnetic cycles, and you think of a cosmic ray entering a mess like this, it's not clear sometimes that some of these simple models work very well. But I thought I'd throw this in just to put some doubt in your mind that some of the simple models that one uses are perfectly valid. Although I think they capture the essence of things like modulation. But anyway, as I mentioned, the thing about the modulation is that the low energy particles don't get in. They lose energy and they don't get in. And so the result is that until Voyager left the heliosphere, and this I showed this morning, we didn't really have any idea what the cosmic ray spectrum was like at those low energies. And now we do, because we're actually out there. And this is uninfluenced by the effect of the heliosphere. And so here's some level here, and let me just show a couple of spectra. And people were totally excited about this. I mean, this is not my area, so but there were a lot of people who wanted to compare with their predictions. And these are the rollover spectra. This is out to this is MeV per nucleon, so out to a GeV. And these are the, what is this? Yeah, hydrogen, helium, carbon, and oxygen. And so, again, these had never been seen before. And the electron spectrum was also, and you know, these low energies are interesting too because they different processes which roll out in interstellar space, which roll over the low energy cosmic ray spectrum. Ionization, for example, just passing by material which you can excite if you come close, and ionization of close by material. And in these kind of processes, the cosmic rays lose a little bit of energy, and trying to get the rollover correct, of course, requires that but we had no idea how important those processes were. Okay, and then here's the electron spectrum, was also something that was completely unknown until the Voyager. And here's the kind of culprit that apparently accelerates the particles up to the knee in the spectrum. Here's an image. I don't know what the image is in, but you actually, in this wavelength, you get a feel for, this is all this turbulence inside, but you get a feel for this very smooth kind of object around here, which is presumably the shock wave. Oh, this was this thing by Luchek and Bell about magnetic field amplification, which helps the efficiency of supernova acceleration of cosmic rays. Okay. Oh, and this is kind of a nice view to show you where cosmic rays are when the cosmic rays roam around the galaxy. So, you know, they're accelerated all these supernovae, and they roam around in the halo of the galaxy. And eventually they, in the process, they can create secondary, they have some interactions. They create, by collisions, they'll create some of the rare species that are not in the primaries, like lithium, beryllium, and boron. There's a whole story here in sort of predicting their spectra. Those species, through the process of the secondaries, like lithium, beryllium, boron, have a softer spectrum because it takes them longer they spend less time in the galaxy. Eventually, of course, when they pass through the disk of the galaxy, okay, which is, you know, if you're viewing into the disk of the galaxy, what you see is gamma rays. I don't remember what the energy of these is, but the Fermi mission, which is up now, has the incredible measurements of the gamma ray flux. And coming from the disk, which is basically, that's where the gas is, and cosmic rays bash into the gas and create gamma rays, and this is what you see. So you see basically a locale for where the product of cosmic ray density and gas density is maximum, and it's along the disk. There's obviously some individual sources, like the pulsars sometimes, Cygnus region, but this diffuse stuff is simply coming from cosmic rays roaming around in our galaxy, bashing into the gas. And eventually they escape, you know. The magnetic field of the galaxy is fairly complex. It's mostly held down by the gas, but it has loops that go up into the so-called halo. Cosmic rays will, of course, being very mobile, circulate around in the halo. Sometimes many escape. If they get, you know, they can blow open a loop of magnetic field, or they come back down, or they end up in one of our detectors. And the typical lifetime of cosmic rays is something like 10 million years. In 10 million years, they generally either bash into something or they escape. So anyway, so that's galactic cosmic rays. All right. Okay. Thanks very much for your attention. All right, any questions? Anyway, you'll have all these slides, and I hope the derivations on the Parker equation and the focus transport will be useful if you happen to do any research in that area. And I've made reference to the 4 exercises that you might find fun to go through. So I hope that will be entertaining.